All right, hello. We are jumping into skill 3. You can find it in section 14.7 in your textbook if you need more information than what you're going to get right here today. Okay, and we're dealing with double and half angle formulas. Okay, so half angle, there is one for sine, one for cosine, and one for tangent. And we'll start with sine. Okay, so sine double angle, this is what I mean by double angle, is equal to 2 sine theta cosine theta. Okay, and what I mean by double angle is, let's say we're trying to calculate 240 degrees, we would break that to be 2 times 120. It's a double angle. Okay, 120 plus 120. So sine of 2 theta. Cosine actually has, you're welcome, actually has 3 different versions. The main one is cosine squared minus sine squared theta. And if you remember from skill 1, the Pythagorean identities, cosine squared can be rewritten as can sine squared. And so we're able to derive 2 cosine squared theta minus 1 and 1 minus 2 sine squared theta. Okay, so all 3 of those can be used to find a cosine double angle. You could also, sorry guys, you could also use all 3 of these to verify identities. Okay, and then the last one is tangent 2 theta, and that is 2 tan theta over 1 minus tangent squared theta, whatever theta might be. Okay, and why they work? Well, 2 theta, the example I gave you guys was 240 degrees, right? So 2 times 120. 120 plus 120. Well, let's say that I have sine of 1 theta plus 1 theta, ultimately 2 theta. Here, I'll rewrite it. Okay, so let's say we have sine of 2 theta, right? That can be rewritten as the sine of theta plus theta. Okay, just like x plus x is 2x, theta plus theta is 2 theta. Well, thank you, skill 2. Our sum formula we know is going to be sine theta cosine theta, because that's the first and the second angle. Same operation, cosine theta, sine theta. Well, these are identical, so we would then have 2 sine theta cosine theta. Boom, there is your double angle formula. Okay, just to do the cosine one for you, it's the same idea. Okay, cosine 2 theta. If I have cosine of 1 theta plus 1 theta, I have 2 thetas. All right, well, the sum formula for cosine is cosine theta, first angle, second angle, minus, because it's the opposite operation, sine theta, which leads us to cosine squared theta minus sine squared theta. Boom, there's the first one. Now, I did mention that cosine squared theta and sine squared theta can be rewritten because of the Pythagoreans. So if we play with that, let's change sine squared theta to be 1 minus cosine squared theta. Distribute the negative like we normally would, so minus 1 plus cosine squared theta, and we end up with 2 cosine squared theta minus 1, which is the second option for the cosine double angle. Kind of cool. I know, not everyone appreciates it like I do, but I think it's pretty awesome. So that's where they come from. It's from the sum formulas, because if I have a theta plus theta, I have 2 thetas. What if I am doing my half angle formulas? Okay, what do those look like? Well, for sine, and a half angle is just that. It is an angle divided by 2. It's half of an angle. That is alpha. Okay, alpha, beta, theta, x. We use those for the angle measurements. And for sine, it is plus or minus the square root of 1 minus cosine alpha all over 2. Me again. I'm sorry about the cough. And so that plus or minus is determined on whatever angle we're trying to find. I'll talk about that in just a sec, all right, after we get these down. Cosine half angle, so alpha over 2, is going to be equal to plus or minus the square root of 1 plus cosine x all over 2. And then tangent of our half angle is again plus or minus the square root of 1 minus cosine of x over 1 plus. Oh fudge, I gotta keep that consistent. Sorry guys, we're not dealing with x. What am I thinking? That is definitely alpha. Please keep your angles consistent. There we go. And so something to note as you're memorizing these, for sine, okay, sine is subtraction, okay, cosine is not, and then tangent is sine over cosine, so subtraction over addition, something to think about. Okay, so let's say that we wanted to find the sine of, I don't know, 60 degrees, and we didn't know it, right? We could use the sine, actually let's do sine of 30. And let's say you didn't know it. You could use the half angle to say the sine of 60 over 2 and then use the formula from there. But be careful because we're not finding 60, right? We're finding the sine of 30 degrees. We're using the half angle to calculate that. So since sine of 30 is in our first quadrant, we would then use the positive one, not the negative. So you might want to make a little note somewhere that it's up to you to decide where, if it's plus or minus. Just doing the calculation mathematically is not going to decide that for you. You're going to have to do some analysis, and we'll have some examples of that. Okay, so why do these work? Well, I'm going to let theta equal alpha over 2, and these half angle formulas actually come from the double angles. It's pretty fantastic. We have to say that theta is going to be alpha over 2 because let's use the cosine one. Okay, so we have the cosine double angle, and for our purposes of deriving the half angle, I'm going to use 2 cosine squared theta minus 1. Okay, I've already said that theta is alpha over 2, and I'm allowed to change that as long as I state it, and we did. So everywhere there is a theta, I'm going to substitute alpha over 2. Okay, so that's in the first, and then that becomes in the second as well. Okay, well, these 2's are going to cancel out, so we end up with cosine of alpha is equal to 2 times the cosine of alpha over 2 squared minus 1. Remember, we're trying to derive the half angle formula from the double angle. So I'm going to start moving some things around. I'm going to add 1 to both sides is equal to 2 times the cosine of alpha over 2 quantity squared. And then I'm going to divide by 2. So we have this cosine of alpha over 2 quantity squared equal to 1 plus cosine alpha all over 2. Commutative property says I can move things around as long as I keep the signs the same, and I did. And then the last thing we need to do is take the square root. So our cosine half angle is equal to plus and minus the square root of 1 plus cosine alpha all over 2. Dun da da! Yes, that is why they work. It's pretty rad. And the cool thing is if you play around with it, they actually all come from the cosine double angle. Sine does as well. If I were to, well, let's do it, right? Okay, so we are going to say let theta equal alpha over 2. So I'm going to pick the cosine double angle with the sine squared theta. Okay, so we set the stipulation that theta is alpha over 2. So I'm just going to substitute in alpha over 2 squared. We already know that these are going to cancel out. Okay, so we get cosine alpha is equal to 1 minus, am I missing a 2? Poop, I totally am. Go ahead and add that in for me, you guys. Okay, minus 2 times the quantity sine alpha over 2 squared. And we're trying to solve for this half angle, right? So I'm going to subtract 1, so we get cosine alpha minus 1 is equal to negative 2 times the quantity sine alpha over 2 squared. Yep, I'm going to divide everything by 2, so we have the quantity sine alpha over 2 quantity squared is equal to cosine alpha minus 1 all over negative 2. Well, if the negative comes up to the top, it changes some things. So we have the quantity of sine alpha over 2 squared. This is now becomes a positive 1 minus cosine alpha all over 2. and then take the square root. Those cancel, so we get sine alpha over 2. The half angle equals plus and minus, and that, ladies and gentlemen, is why that one, oh, I don't need to box it, is minus subtraction. Okay? Yes, pretty cool. All right, let's get into the good stuff. How do we use this? Well, we can use it to derive some identities. Okay, so how can you derive the following identities? Tangent 2 theta equals 2 tan theta over 1 minus tangent squared theta. Well, let's say you don't believe me. You know what, Patterson? I think you're lying. Okay, you know what? Touche. Let me prove you wrong. Let's use the same idea that we did when I was showing you sine and cosine up here. Okay, so tangent 2 theta, I'm going to rewrite that as tangent of theta plus theta, which we can do. Totally nothing wrong with that. We know x plus x is 2x, so theta plus theta is 2 theta. Okay, so then using the sum formula for tangent, we get tangent of the first angle, which is theta, plus tangent of the second angle, all over 1 minus tangent of the first angle times tangent of the second angle. Finishing that out in the numerator, you get 2 tan thetas, all over 1 minus tan squared theta. So you're starting to see, hopefully, that little by little we've introduced you to these identities, and you can interchange them and use them to derive each other, which is pretty neat. It shows that they're all interconnected. Just like when we completed the square and we derived the quadratic formula, and we were so excited. Okay, so don't lie, you were excited. I was excited. What is the exact value of sine 270? Use a double angle identity. Okay, very specific directions. Use a double angle identity. So we know that sine of 2 theta, looking back at our handy dandy notes that we just took, is 2 sine theta cosine theta. And we need to figure out what theta is. Well, I'm supposed to use a double angle identity, and I need 2 theta to be 270 degrees. I'm not trying to make some funky new change, right? We genuinely need it to be 270 degrees because that's what's given. So if I cut this in half, I'm going to get 135 degrees. So our theta is going to be 2 times, our theta is going to be 135 degrees. That's what we'll plug into the identity. So when you're asked to use a double angle identity, you need to cut the original angle in half to find what your theta is going to be. So this is 2 times the sine of 135 degrees times the cosine of 135 degrees. Okay, thinking about our Cartesian coordinate plane, right? 135 degrees is in the second quadrant, and, draw it all out for you, it has a 45-degree reference angle. How did I know that? Because it's 45 degrees away from hitting 180, from getting to that x-axis. So I can then substitute in 2 times the sine of 135 is a positive rad 2 over 2, because I'm in the second quadrant, and the cosine is a negative rad 2 over 2. If I multiply, well, I can reduce one set of 2's, and I get a negative square root of 4 over 2, which is a negative 2 over 2, which is negative 1, and we know that the sine of 270 degrees is negative 1. So yes, it's nice because we already know it. Some of you might be frustrated because you already know it, but it's good because we can double check. Did we use the double angle identity properly? And yes, we did, because we got the answer we knew we should have. Nicely done. Okay, example number 3. I'm going to switch colors again. Use or verify, the following identity. So sine of 2 theta is equal to 2 tan theta minus 2 tan theta sine squared theta. A lot going on here. Okay, things to keep in mind. Sine of 2 theta is equal to 2 sine theta cosine theta. So ultimately, this is what we're trying to achieve. Okay, I'm going to work with the right-hand side because there's a whole heck of a lot more to work with. And I'm going to change it to be 2 sine theta over cosine theta minus 2 sine theta over cosine theta times sine squared theta. If I change everything to sine and cosine, Okay, I might be able to pull something out of this. And let's see where we can go from here. Okay, so if I multiply this, right, we end up with 2 sine theta cosine theta minus 2, ignore that 2, sine cubed theta over cosine theta. Okay. Right away I notice they have something in common, so I'm going to go ahead and pull out a 2 sine theta over cosine theta, because they each have that, and I'm left with 1 minus sine squared theta. Sine over cosine is tangent, so I get 2 tan theta times cosine squared theta. Okay, I'm actually going to, and you can do this, it's okay, I'm going to go back to sine theta over cosine theta. I'm not changing my process, I'm not changing my steps, I'm just changing the format in which it's written. And the reason is because I see that I can reduce one of these, and I'm left with 2 sine theta cosine theta, which we know is sine of 2 theta. So I'm going to write my, oh my gosh, why do I keep writing a 2? Okay, I'm going to write my final statement. Sine of 2 theta is equal to sine of 2 theta. Nice. Okay, now you might have looked at this and said, okay, I could have at the beginning factored out a 2 tan of theta. Yeah, absolutely, you could have. And we would have gotten the same answer. So again, with these identities, you guys, there isn't just one way to do it. Okay, oftentimes there's an easier way, but again, that's really subjective, okay? So play around with it. If you don't like something, stop and do it over again from a different angle. Okay, example 4. Get it? Angle? Totally didn't even mean to make that funny. That's amazing. Okay, example number 4. What is the exact value? Use the half angle. All right, for the double angle, we had to take what was given and cut it in half. For the half angle, okay, we're trying to find the tangent of 195. I didn't actually need to write tangent. That was the given, right? So 195 degrees. And we need to figure out how to put that into a half angle formula. Okay, so I'm going to double it. Very good. So our alpha is going to be, what is that? 390 degrees. But remember, this is what we're being asked to find. Okay, so tangent alpha over 2 is plus and minus the square root of sine over cosine. So subtraction over addition. And we'll deal with the plus and the minus at the end. Okay, so ultimately, and I'm going to go this way, tangent of 390 over 2. We're trying to find the tangent of 195, which means we had to use the half angle and double the original, okay? If you're asked to use the double angle formulas, you have the original. If you're asked to use the half angle identities or formulas, you double your original, okay? All right, so here we go. Plus or minus, we're not really sure. 1 minus, 390. Well, think about your Cartesian coordinate. Go around 360, boom. 390 is right there. It has a 30-degree reference angle. So the cosine of 390 is the same as the cosine of a 30-degree reference angle, which is rad 3 over 2. Good, okay. So we have 1 minus, come on, there we go, rad 3 over 2 all over 1 plus rad 3 over 2. Oh, this is going to be pretty. So what I'm going to do is I'm going to split it out because you know that's my preference. Okay, so I'm going to get common denominators, and that means that we have 2 over 2 minus rad 3 over 2 being divided by 2 over 2 plus rad 3 over 2. Okay, I just split it out because I don't like having fractions over fractions with more fractions to add and subtract fractions. All right, follow my arrow, please. We have plus and minus the square root of, well, 2 minus rad 3 all over 2 being divided by 2 plus rad 3 all over 2. Just combine the fractions. And then we can plus and minus square root apply 2 minus rad 3 over 2 times the reciprocal. 2 over 2 plus rad 3. Now these are going to reduce to 1. So we end up with plus and minus the square root of 2 minus rad 3 all over 2 plus the square root of 3. But we cannot leave a radical in the denominator. So back in the day when I actually saw you guys in the classroom, we learned about multiplying by the conjugate. The conjugate is the same the same binomial, opposite operation. And the reason why we like this is because in the foiling process, we don't have to OI. We could just multiply the first and the last because the OI canceled out. All right, so we get plus and minus. Foil the top, we get 4 minus 2 rad 3 minus 2 rad 3 plus 3 all over 4 minus 3. Keep going with me, we're almost there. Plus and minus the square root of 7 minus 4 rad 3 all over 1. So we get this beautiful plus and minus the square root of 7 minus 4 rad 3. Now the good news is we are almost done, but we still have this pesky plus or minus, right? Remember, we were asked to find the tangent of 195. Using the half angle formula, we used 390 as our alpha, but 390 is not ultimately what we're finding. So if we think about our Cartesian coordinate plane, and this is 0, and this is 90, and this is 180, and this is 270, 190 is right about right here, where tangent is positive. So we are going to have a positive square root of 7 minus 4 rad 3. Oh, that's nice. So nice. Yes. All right. Last but not least, given, this is a different type of problem, okay, given that the sine of theta is negative 5 over 13, and theta is between 270 and 360. Okay, so right then and there, I know that I'm in the fourth quadrant, so I'm going to draw a triangle as if I was in the fourth quadrant with theta right there. And it tells me that sine is negative 5 over 13, so opposite has to be the negative because the hypotenuse is always positive. If you were to use the Pythagorean theorem, you would find that this is 12 and it's positive because in the fourth quadrant, the x-axis is positive. Okay. So now it's asking for the tangent of theta over 2. Tangent of theta over 2. It's not asking for the tangent of theta. It's asking us for the tangent of theta over 2. Theta is in the fourth quadrant. Theta over 2 is between 135 and 180. Which is in the second quadrant. Okay, so we have to be really careful. We're not asked, oh gosh, sorry, I'm hitting a paper. We're not asked to find the tangent of theta. Like, okay, example number 4, tangent of 195. We then used theta over 2 to solve our problem. Here, we're being asked to find the tangent of theta over 2. Theta over 2 is in the second quadrant. Tangent will be negative. Okay, we'll remember that for our final answer. So here we go. So tangent of theta over 2 is plus and minus the square root of 1 minus the cosine of, theta? What am I thinking? Sorry, guys. Over 1 plus the cosine of theta. Okay, cosine of theta comes from the original given information, right here that we built our triangle from. So we know the answer is going to be negative because we divided the given theta restrictions by 2 because we're asked to find theta over 2, not theta. And we have the square root of cosine of theta is going to be 12 over 13. So 1 minus 12 over 13 all over 1 plus 12 over 13. Okay, again, because I don't like having fractions over fractions being added to more fractions, I'm going to split it. So we have a negative square root of 1 minus 12 over 13 divided by 1 plus 12 over 13. Travel with me, if you will. Getting common denominators, I'm going to have 13 minus 12. Let me write it out for us fully. There we go. Divided by 13 over 13 plus 12 over 13. I still have a negative on the outside. Don't forget that. So we have 1 over 13 divided by 25 over 13. That becomes a negative square root of 1 over 13 times 13 over 25, because we keep the first fraction changed to multiplication and take the reciprocal of the second. The 13's reduced, so we get a negative square root of 1 over 25. Final answer is a negative 1/5. Yeah! So 2 different situations, you guys, where you're being asked to use the half angles and where you have to determine if it's plus or minus. If you're asked to find a trig function for a given angle, use the location of that given angle. But if I'm given information from which I then have to create a triangle somewhere on the Cartesian coordinate plane based off a set restriction for theta, and then it asks me to find tangent or sine or cosine of theta over 2, you're finding the half angle, then you have to cut the restriction in half and use that correlation. All right, good luck.